I don't know how far we're going to get here. I think we've kind of passed the point where I can say, oh, you know what, I'm just going to push through and do the whole lesson. I don't think that would be wise. So we'll make some adjustments later. But we're moving now into chapter 10, which deals with area. And what we're going to be doing, what this lesson culminates in, is being able to find what we call simple areas bound by a function and the x-axis over a specific interval. And we'll get to what that looks like in a bit. Normally, I would teach this to you by telling you the answer to a problem and then proving the answer, but I've decided this semester to go the other way. We're going to develop the answer to the question together. And I think what we're going to work through today, I'm always amazed by it. I'm always blown away by the result. So, we have this area problem. It's kind of like the tangent problem. We had the tangent problem. How do we determine the slope of a tangent to a function at any point on the function? There was a problem. And that led us to derivatives and this whole branch of calculus called differential calculus. Well, we have an area problem now, which is going to lead us to what are called integrals, which leads us to integral calculus. A function is both positive and continuous for x greater than 0. I think if I had to retype this, I would say greater than or equal to 0. Okay? So what we're talking about is a function that looks like that. It doesn't have to have that curve, but what is important is the function is positive everywhere. It doesn't matter, but I'm going to say everywhere including 0 and to the right of 0. And here's the problem. How can we determine the area above the x-axis, below the function, and between the lines x equals 0 and x equals some other number, x? That's what the problem is. And again, I'm amazed by this, that we're able to come up with an answer to this question only because somebody in the distant past has come up with a strategy for determining it. Can I show you the strategy? But it's an amazing feat. So this is the problem. What is the area? And here's how we're going to start. And I've got a line up here to remind me that I'm going to be at some point a little bit later writing some information to the left of the y-axis. So when you write stuff down, I don't think that's going to be an issue for you based on how it's formatted. That's just there for me. What I'm going to do is I am going to define this area to be a function of x. And you need to think carefully about what this means. I'm telling you that in order to determine the area between 0 and some x coordinate, you have to know what that x coordinate is. It makes sense that that area depends on the x coordinate. So for example, if I know what this function is, and I won't even bother writing it down. If I know what this function is, a of x, and I find a of 2, I put 2 into a of x, I will be finding the area between x equals 0 and x equals 2 for this type of function that's positive and continuous. If I put in pi, if I find a of pi, what I will be determining is the area between 0 and pi of this function that is continuous and positive in that interval. So I'm defining the answer to the question, basically. I'm saying this is the answer to the question, a of x. And what we're going to do is we're going to take the derivative of that area function. And the first question that should pop into your head is, why on earth would we do that? And the answer is because somebody far cleverer than myself has figured out that this leads somewhere. This is actually what we're going to be eventually demonstrating here is actually called the fundamental theorem of calculus. It's a big deal. So how do we determine the derivative of a function if we don't know the function? Well, we use the definition of the derivative. The derivative of any function is the limit as h approaches 0 of the function at x plus h minus the function at x all over h. So a prime of x is going to be the following. It's going to be the limit as h approaches 0 of a of x plus h minus a of x all over h. All right. I'm going to introduce some notation now. Rather than me writing a of x by definition, if you look at this diagram, is the area between 0 and x, right? So in my next line, instead of writing a of x, what I'm going to do is I'm going to write that. This is just a way for me to say that term is the area from 0 to x. And by the way, if you look at proofs online or you look at proofs in a calculus textbook, they are a little bit different. I've changed something here to suit high school needs. Okay? Now, what is a of x plus h? Well, wait a minute. And by the way, this demonstration, there's not a lot of algebra to it. It's logical. I told you a of x is the area from 0 to x. And a of 3 is the area from 0 to 3. And a of pi is the area from 0 to pi. Well, that means a of x plus h is this. It's the area from x equals 0 to x plus h. Which means now we have the derivative of the area function. The derivative of the area function is equal to the limit as h approaches 0 of the area. So it's all of a sudden gone from algebra to geometry. The limit as h approaches 0 of the area between x equals 0 and x plus h minus the area between x equals 0 and x, all over h. But the area between 0 and you don't have a bunch of highlighters, so you're going to have to figure out a way to communicate this to yourself, or you can watch the video later. The area between 0 and x is this. Right? Now, what is the area between 0 and x plus h? Well, we don't have an x plus h, but you will notice I have a line here. And I would like you to draw a vertical line approximately in that position. You want it just in that position because a little bit later we're going to be doing something with the curve that requires it in that approximate position. This position here, by the way, is at x plus h, and it can be anywhere to the right of x. And I hope everybody understands the distance between x and x plus h is h. Right? What do you add to x to get x plus h? H. This width of this clear area is h. But what that means, everybody, is that this is the following. And I'm drawing that outside, particularly on the left of the diagram, so that it doesn't overlap with the blue so that you can see that. And there's a number of ways to proceed from here, but let me just write it out because I think it's, if you think about it, it becomes quite obvious. That this will now be the limit, and I have to move that down a bit, I didn't give myself quite enough room, will be the limit as h approaches 0 of the following area. It has to be the area between x and x plus h. I mean, ask yourself what you would get if you took the area that is bound by that green highlight that I've made, and you subtract the area that's bound by the blue. Well, what you would get is this area. We can reverse engineer this, so to speak, by saying the blue area plus the yellow area would give us the green area, which means the green area minus the blue area. And don't forget, the green area is the area highlighted in green, that's A from 0 to x plus h, minus the blue, which is the area highlighted in blue, which is A from 0 to x. When we subtract those, we get that. You get the area between those 2 points. And I know that you still don't know why we're doing what we're doing. But again, the result is going to be amazing. I'm really blown away by it every time I see this. So this is the problem. How do we find the area of this yellow shaded part? And we're going to talk about approximating the area. And this is where we look at the bottom of your handout. And I have 2 diagrams. They're under the heading, approximations of the area between x and x plus h. So let's not worry about what the precise area is. We're trying to find out what this area from x to x plus h is so we can put it in here and see what happens. Okay? And again, it seems really weird because we don't even know the function. It doesn't matter. So on the left-hand side of what's on the bottom, you have a diagram that's labeled too small. And that's the diagram I want to talk about. If you really stretch your imagination, would you agree that that yellow highlighted area is rectangular-ish? Somewhat. It's not a perfect rectangle. Well, a rectangle is a nice shape to find area from because it's really easy, length times width or base times height. So what I'm going to do, and I want you to draw in what you're going to see here, is we're going to use the left-hand side of that interval, whose area we want to find, to define the height of a rectangle. So if I draw a rectangle whose height is equal to the height of the function at the beginning of the interval, I get that rectangle. Yeah? Would everybody agree that the area of that rectangle is too small? It is going to be a smaller area than the area of the yellow highlighted region because it's going to be missing this wedgy kind of shaped piece at the top. Okay. Nevertheless, how would we find that area? Well, it's length times width. We know the width of that, it's h. So the width of this rectangle is h. And we know the height is going to be f of x. And I want to point out the height is not f of x because the function is f of x. The height is f of x because x is the x coordinate of this point, so the y coordinate is f of x. The height of that rectangle will be f of x. And that means that the area of that rectangle that is not the right area is f of x times h. All right, which again is too small. And you notice that I put less than, which means it's really too small. It's not even close. Now, if the function is sloped less, maybe it's closer. If we use the left-hand side of the interval and the height of the function at that left-hand side to define the area of the rectangle, our approximation is too small. Are you with me on that? So now let's shift gears and let's look at the diagram on the bottom of your page to the right, where it says too big. I'm focusing on this one. What if instead of using the left-hand boundary of the interval to define the height of the rectangle, what if we look at the height of the function on the right-hand side? So now I'm focusing on this point up here, right? And I construct a rectangle with that height. So you're going to have to draw in this rectangle. while you're drawing that, I can continue talking. I think everybody would agree that the area of that rectangle is too big because it is now including all of this which we do not want to include, right? Now, nevertheless, how would we calculate that area if we wanted to? Well, it's length times width, but again, the width is h. And you can see that I put the area of the rectangle is really big compared to what we want. What is the height of that rectangle? Well, the height of the rectangle is not f of x, it's f of x plus h. And this is going to come together quickly because I can see some of you looking at the screen kind of with puzzled looks on your faces, and I understand you're probably saying to yourself, where is this going? And it will happen quick, but not for a minute or two. So what is the area of that blue outlined rectangle? It's the height times the width, which is f of x plus h, times h. Still with me? It's too big. So we're still talking now about what's at the bottom of the page, but you don't need to write anything for a while. If we define the height of the rectangle to be f of x, which means we're using that teal or cyan colored point, we get an area that's too small. And if we define the end of the function in that interval to be the height, we get an area that's too big. But what if we pick a point in between? What if we pick that point and I say whatever that height is, let's construct a rectangle. Now you don't have to draw this, I just want you to think about it. Because normally the proof or the demonstration here would just be verbal. You wouldn't even write anything. Then it's that rectangle. It's not this one. It's not this one. It's this one. Now, is the area of that blue rectangle, based on what you're looking at, equal to the area that's shaded yellow? No. It's still too small, isn't it? But do you see that it's closer? Because now it's including a little bit of area in here that we don't want, and it's missing some area here that we do want, but it's not missing as much as it was before. Anyway, we call this point C for x, and it's really crucial that you understand no matter what we do, C is between x and x plus h. It has to be. It doesn't matter how far away from x plus h is, C has to be somewhere in between. What is the width of this? Well, the width is h. What is the height? The height is f of c. So the area of that rectangle, which is our rectangular approximation, is f of c times h. It's still too small though, right? Well, watch carefully on the screen. What if I take that point, that where x is c, and I just nudge it over a bit to the right? The area will still be f of c times h, but it's closer, isn't it? Is everybody with me on the concept that if we can make this area the same as this area, then everything will be perfect? That's the goal. So what if I nudge this point over a bit more? That's still too small. What if I nudge it over? Okay, do you agree that at this point in time, the area will be too big? So we're looking for that ideal point. And the logic, everybody, I want to see where I am. The logic is this, and there's a theorem for it that we'll get to in a second, that if this is too small, using x as the input for the height of the function, and using x plus h is too big, there has to be a point in between x and x plus h that is perfect, kind of the Goldilocks zone. So now we're going to get back to the top of the page. So this was what we've done so far. You don't need to write anything just yet. We've said that I want to find this area. I'm going to take the derivative of that function, which is equal to this. This can be written as a from 0 to x. This can be written as a from 0 to x plus h. We need to introduce an x plus h. The blue area is that. The green area is represented by that, which means that the top of that is the area between x and x plus h, which is the yellow portion. That's where we left off. Still with me? Okay, so now pencil to paper again. How is it we determine what that is? Well, you'll want to maybe just wait and see what I draw first before you draw anything. We know that if the rectangle is that high, we don't get enough area in that rectangle. And we know that if the rectangle is this high, we get too much area. So what I'm doing is I'm kind of eyeballing where I personally think, and it doesn't have to be perfect because we're going to be doing algebra here in a second, where I personally think the balance would be. And I'm going to go with that. I've drawn a curve, by the way, so that you don't learn a misunderstanding that that critical point for C is halfway between the beginning and the end of that boundary. It doesn't have to be halfway in between. Depends on the shape of the curve. So if I were to construct a rectangle now, and you can go ahead and draw this, I think that's not bad. It's hard to judge areas that are curvy like this. But I'm thinking that this is an extra area, and this is an area I'm neglecting, and I think they're equal in magnitude, so I'm saying that that looks pretty good. Are you with me on the principle of this? Okay. Well, we need to define the location of that. So you're going to draw a vertical line down from this point of intersection and label that as C. Okay, so now what? Well, you can also draw a horizontal line over from that point so that you can understand or write that this is f of C. So what is the area of the highlighted portion, which is equal to the area of the blue rectangle because it's a perfect fit? Well, it's the length times the width. Well, the width is h. And the length, or the height, is f of c. So the numerator of this limit is f of c times h over h, which is f of c, because the h on the top and the bottom cancel. Okay. The derivative of the thing we are trying to find, we're not trying to find the derivative of a of x, we're trying to find a of x, is equal to the limit as h approaches 0 of f of c. What does that mean? Well, let's talk about what's happening to these two things as h approaches 0. We can talk about all three things, but x doesn't move because we started off with x being the value that's the input for the area function. It's x plus h that's crowding in on x. So what's happening is this, that we have x plus h, and we have c, which is somewhere in between here. It doesn't matter where we draw it. and h is approaching 0. I want to go back and talk now about the fact that c is always between x and x plus h. It doesn't matter how close x plus h is to x. C must be sandwiched between x and x plus h. In fact, the theorem we're using to finish this is called the sandwich theorem or the squeeze theorem. If h approaches 0, then that has to be true. It has to. But if x plus h is approaching x and c is always sandwiched between the two, that means c has to approach x. If c is approaching x, it's because h is approaching 0, and x plus h is getting closer to x. This is called the sandwich theorem or the squeeze theorem. And there's kind of an algebraic approach, but in high school I would rather just leave it in words. What that means, everybody, is that when we have a prime of x is equal to the limit as h approaches 0 of f of c, we can rewrite that as that. Saying h approaches 0 in this context is the same as saying that c approaches x. Now let's think about this for a second, and I think I'm just going to write this on the sideboard. If I have a limit as heart approaches something, and it's a limit of 1 over 3 plus that thing, you replace that thing with the heart. Which means the limit as c approaches x of f of c is f of x. We're putting in the value that c is approaching. Just like if it was, it's a little bit weird because normally limits are x approaching a number and you put the number in. This time it's c approaching x, so we put x in. I love this. To me, it's fascinating. The first time I saw this, I was in awe. What this is saying is that there's a function to calculate area for every function in the universe, as long as it's continuous and positive, whose derivative is equal to the function whose area you're trying to define. Now, the only issue is the problem was this, wasn't it? Well, how can I change a prime of x to a of x? I can anti-differentiate. But that means I have to anti-differentiate the other side as well. To me, that is absolutely amazing. That what we have proven is in order for you to find the area from x equals 0 to any value of x under these conditions, you put that value of x into the antiderivative of the function. And this is the first part of what we need to know or learn today. There's another part that I'm leading up to, and that's why there's no way we're going to get through this whole lesson. Okay. So, I mean, you can go back if you like and take a look at your original diagram here. That's it. Take the function and anti-differentiate it, and then put in the value of x whose area defines the end, or that defines the end of the area, and you have the area. I think if you were introduced to this in post-secondary calculus, it would not walk you through the step to get to here. It would walk you through even further to get to something else that I want to get to. But this is just part one. Okay? Let's take a look now at warm-up part two. Use the rule derived in part one to find the area between the x-axis and y equals 2 over x plus 1 plus 3 from 0 to 5. And you can trust me that this is what the graph looks like. So it is continuous from 0 to 5, it is positive from 0 to 5, and it is an area from 0 to some value of x. What I'm telling you is the area here will be equal to that. That's all there is to it. We've proven that that's the case, so we can now calculate it whenever we want to. Well, that requires, of course, that we find the antiderivative first. And we have a bit of an issue here. Well, no, we don't. This is the part where if you had a proof in post-secondary, you wouldn't run into this problem. I guess I'm just going to have to tell you we ignore the constant, and you will see why in a bit. Okay? So, that's the antiderivative. Would you agree? Okay. So that means the antiderivative at 5 will be 2 ln 5 plus 1 plus 3 times 5. So we get the area equals 2 ln 6 plus 15. Let's calculate what that is. So what 1 square unit of area means is 1 xy's by 1 yy's, a rectangle that's 1 by 1 on the grid. Okay? 2 ln 6 plus 15. And I'm getting 18.58 something-ish. We can write that down or not. That's not my point. If you did write it down, you'd put approximately equal to. The question said verify with your graphing calculator. So I'm going to put this into my graphing calculator. The function, which is 2 over x plus 1 plus 3. I'm going to adjust my window settings to reflect kind of what we're looking at here. And I will tell you what the vertical aspect is going to be. What do we have for a function? 2, 0, 2. I would say if we go up to about 4 vertically, it will be fine. So I'm going from 0 to, well, you know what? Let's go from -1 to 7. And let's go from -1 to 6. Doesn't matter, you could adjust it later. So this is what the function looks like. Pretty good representation. Now, we can find the area on our calculator. Unfortunately, the notation is different. And we'll learn about the notation in the coming days. You go to your calculate menu, and you choose option number 7. And there's an S there, kind of an elongated S, an f of x dx. That has something to do with the antiderivative. And it says lower limit. Well, that just means where are we finding the area from? From 0 to 5. So we enter 0, hit enter, enter 5, hit enter, and a very glorious thing happens. Not only does it calculate the decimal area, it shades it in so that you can see it. And that matches, right? So it works. If it didn't work, we wouldn't have gone through that exercise, but it works. Let's try another one. Warm up part 3. Use the rule derived in part 1, which is, I'm going to repeat it for you, that the area between 0 and x, as long as the function is continuous and positive, the area between 0 and x is the antiderivative at x. What we want to do is we want to find this area. This is the area we want to find. And the issue here is that this area is not an area between 0 and x. But I can find this area, which is the area between 0 and 5, or f of 5, and subtract from it this area, which is the area between 0 and 2, and that should leave me the area between 2 and 5. And in post-secondary, you would have proved this right out of the gate. You wouldn't have done from 0 to x. That's what I've changed. But that means that this should be the antiderivative at 5 minus the antiderivative at 2. Should be.
Why is this from 2 to 6?
It's from 2 to 6?
Yeah.
Okay. Thank you. Let me just change this up here. Give me a second, because otherwise I will forget to change it later. I'm sure that didn't cause you undue concern having me as a teacher as long as you have. You're with me on this? Okay. So what is the antiderivative? Well, we can calculate that kind of wherever we want. The antiderivative would be 1/12 x cubed plus x. I just want to double check that. You can double check it as well, but I think that's right. Here is why we can ignore the constant. It's because the antiderivative at 6 will have a constant in it, and the antiderivative at 2 will have the same constant we're subtracting. In reality, the area from 0 to x is actually this. It's the part that I kind of don't like to talk about too much, because then the proof or the demonstration gets incredibly complicated. We have to introduce other letters. It's a mess. Okay? So when we're finding the area, we ignore the constant. So I need to put in to 1/12 x cubed plus x 6 and subtract what I get when I put in to 1/12 x cubed plus x 2. And of course, because of this subtraction sign here, you better make sure that that second calculation is in brackets. I'll give you a minute to run those numbers and see what you get. And I'm just running this through my head, but I'm getting 21 1/3. I'm not getting a lot of positive feedback from you on that. Is it 21 1/3? 21.3 repeating? Okay. So 21 1/3, or let's do it this way, 64 thirds. I should have put square units on the previous question, but that doesn't matter. We're in learning mode right now. So now let's determine this. Let's see if that's right. I'm going to put in a function which was 1/4 x squared, 0.25 x squared plus, was it plus 1? Let me make sure. Yep. Plus 1 could probably get away with the same window settings, I think. We want to go from 2 to 6. Maybe I'll bring this up a bit vertically. So we go to the calculate menu and choose this, which is an area thing, integral, antiderivative, all kind of rolled into one from 2 to 6. Shades it in nicely, you get 21.3 repeating. So everything we have done so far, everybody, leads us to the real rule. This whole from 0 to x thing is for the birds. What we want to do, and if you look at the next page, you will see it, what we want to do is understand the following. That as long as a function is continuous from one value of x to another value of x, and is positive in that interval, in other words, as long as a function looks like that, whether it goes up and down, doesn't matter, the area from a to b, above the x-axis and below the function, will be the antiderivative at b minus the antiderivative at a. That's the rule. And there was a time when I taught calculus that I would have just said, that's the rule, let's get to work. And then I heard back from students after they're in post-secondary, they're really expected to know where this comes from. Okay. That's the rule. It's not given to you as a formula on a formula sheet. You need to know it. So I've decided that what I'm going to do, and by the way, it doesn't matter where the y-axis is. I don't want to get into this, but if the y-axis is here, or here, or here, it doesn't matter. As long as you're going capital F of the bigger, in other words, the right-hand x, minus capital F of the smaller one. I could prove to you that it doesn't matter by demonstrating that if I translate the whole function left or right any arbitrary amount, I will still get the same area because the function will be shifted in terms of x, but all of my a's and b's will also be shifted. It's a net zero change.